Hey everybody, it's the answers to your practice test, and there's a weasel. It's an overhead view of a weasel. All right, let's get these crumbs off of there. All right, let's make it look good for you. I guess we'll put it on there. All right, so problem number one, you read it. Because of the shape, there's no way that I can get the graph. Come on, show up. Oh, I hate this so much. There we go. There's no way I can get the graph to find the area from the curve to the x-axis very easily because that tuck, because that bulge. But if I find the area this way, if I find the area going to the y-axis, that isn't too bad. Plus, I graphed from 0 to pi over 2 to make sure that the integral is finding the piece that I think I'm finding. So you would shade this little first quadrant bulge. That's the shaded area being found. Okay. Oh, look at that. I can actually get it in the picture, sort of. All right, now, but that's an x dy, not a y dx, because you have the y-axis as the bottom. All right. Anyway, so these next few lines are the ones that they gave. Well, if you're doing x dy, then it's x times the derivative of y. So here's the actual pieces. This is my work. And multiplying them out, it does match what's on the page. So you have to multiply out this binomial times this binomial. Matches what's on the page. The page did this next calculation. Didn't have to, but they did because of the cosine squared and the happening twice. You got a couple of cosine squares to deal with. So substitutions there. Could have left this piece alone, but they did a substitution from chapter 7. There's a substitution for when you have a cosine of t times a cosine of 3t. What's nice about it gives you a 2t and a 4t, but that was done on the page. You didn't have to worry about where that came from yourself. But what's nice is just the graph for cosine 2t from 0 to pi over 2 has a positive 1 and a negative 1 bump. So that means that we can now do this. This is a 0. This is a 0. That's a 0. That's a 0. So I made this problem up so you could have the pleasure of killing off almost the entire problem. So for you, you would shade that little piece of curve on the paper, and you would do this integral. Pretty simple integral, not bad, and the answer comes out to be 3 pi, which is a good sized amount. Remember, the curve goes out, past 3, and then it goes up this high, up to 4. So you've got a pretty beefy piece of curve there. So 3 pi is a reasonable answer. All right, next up, we have this derivative, and there's a weasel. Come on over, weasel. Come here. Have a piece of cookie there. She likes fig bars today. Oh, such a good weasel. And let's get rid of the crumbs. All right. So this next one, number 2, you take the derivative, dy dx, and you can simplify it. And at t equals pi over 2, you get a 0 denominator, which means the slope is undefined. Well, that means you don't get a tangent line. You don't get the equation of a y equals mx plus b. You don't get a nice tangent line. You don't have something. And that makes sense because the curve has a cusp at t equals pi over 2. So it would be like having a teeter-totter. You'd have any tangent, any line like this intersects the curve at one point. So there's no one single line that intersects the curve at one point like a tangent curve is supposed to do. Number 3 was the derivative of the cardioid. So you have to multiply the x-coordinate function by cosine theta, the y-coordinate function by sine theta. I'm sorry, you have to multiply r theta. You have to multiply the radius, the function, times cosine. So r is 1 minus cosine theta times cosine theta gives me x. 1 minus cosine theta times sine theta gives me y. That's the way I want to say it. Now, to get dy dx, you have to take the derivative of the y function divided by the derivative of the x function, and that's fitting over here. And I just did an also known as step for you because it happens to be that cosine squared theta minus sine squared theta is cosine 2 theta. So I can substitute in the top for a double angle, and I can substitute in the bottom for a double angle, and you have this nifty, rather simple looking derivative. And there's a weasel coming back up to be with us. Come and be with us, weasel. Look, I got some more for you right there. Isn't this great? Ah, she's just a pig. All right, so that's problems 1, 2, 3. Let's take a look at number 4. So if you studied the trochoid, which if I get a trochoid problem that I can put up on the wiki, you'll have it soon, I hope. But if you didn't, you'd have to do a y equals problem on your calculator. And you probably would have noticed that a factor of 2 is the way to go in this equation. Come on, get nice and dark. There we go. Trying to get this to show up. There we go. The factor of 2 is going to work out great because then you get notches hitting right on the x-axis. So I'm going to graph this for a little bit. Let's see if I get enough of it. Come on, graph it for me, baby. Come on. Oh, it's not graphing anything. Y equals. I got to turn that graph on. All right, graph. Come on. Man, I can see it on my... There it is. Stupid glare. I thought by filming it overhead. All right, so that's the start of it. And it comes bumping on down. Let's go from 0 to that much. Let's see if we get the right shape. So it's graphing now. There we go. There's the graph. Hi, weasel. How you doing? And then notice how it hits the y-axis and just stops. That's good. And then it was going to continue on with a little cusp there. So we've got the right size. So it's going to do this. It's, you know, you're going to graph it looking like this for b equals 2. It's going to go ba-boom, ba-boom. And this guy is at 2 pi. So that's how it goes. Man, that weasel. Come here, Weez. Hey, got a little snack for you. Now, the fifth one is actually trickier than it seems to be because you graph it in polar. It looks like a circle, but you can't just say looks. You know, you can't just say, gee, it looks like a circle. So you have to do some stuff. Come here, you. Come here. Over here. Come on. There she is. Oh, yes. So there's a couple of ways to attack the problem. One is to do the distance between the point sine theta, the point at sine theta in polar, and the center, which is at 1/2 on the y-axis. So I have to multiply sine theta times cosine theta to get the x-coordinate, sine theta times sine theta to get the y-coordinate. So this says cosine theta sine theta, comma sine squared theta. That's the xy coordinate of that point. So I did the distance squared so I don't have the square root. And that's the difference between the x-coordinate squared, and the x-coordinate of this point is 0. So it's this coordinate squared plus the difference of the y-coordinates between these two, quantity squared, multiplied out, and then I took the derivative. This is taking the derivative of it. I didn't actually multiply out, I took the derivative using chain rule. And when I go to take the derivative and simplify, it's a bit of a chore because these terms, you know, because of the chain rule, they get kind of long. But I factored out 2 sine theta cosine theta because everybody had a 2 sine theta cosine theta, and I was left with 2 sine theta cosine theta times sine squared theta plus cosine squared theta minus 1. And we all know sine squared plus cosine squared equals 1, so this whole term is 0. Well, the derivative is 0. The derivative of the radius squared is 0. That means the radius has to be constant. So that's the idea there. The derivative of the radius squared is 0. So the radius is constant. That is a calculus way to show something happens. Now the other option is this. We have the coordinate, the regular xy coordinates for a circle centered at 0, 1/2 would be x squared plus y minus 1/2 quantity squared equals 1/2 squared. That's the equation for the circle. If it's a circle, and we'd like to show it's a circle. So let's just show that any point, and this is the same point I had before, cosine theta sine theta minus, or comma sine squared theta. This is any point on what we want to be our circle fits. That's the word fits. It's not equal it's the word fits. Let's show this point fits. It's actually not too bad. I'm substituting the x and y coordinates into this equation. and I square out this squared piece, and I can factor out a sine squared out of everybody. And look at this, it's our old pal, cosine squared plus sine squared minus 1. So I get a 0 for this complicated piece. So I'm left with 1/4 equals 1/4. So the point fits. That means that any point on this curve fits the equation of this circle. So it's a circle. So that's what's so tough about number 5. You have to think your way out of that jam. It is not easy to show that something is a circle. You have to use some property of a circle. All right, there's your answers. Bye-bye.